Hey again, folks. I'm making another video here to talk about how dynamic library linking works under NixOS. This is I'll just let you know from the beginning, this can be rather dense. And if you're not a video person, you don't learn linearly. I have this script here, which has all the details, will be linked inside of the description of this video. So, one of the, well, I guess probably the main feature of NixOS, just as a end user, is that it solves a problem. And the problem that it solves is something that is colloquially known as DLL hell. And DLL hell exists because in on most systems, only one canonical copy of a shared library or support files or other things is typically imagined to exist on the system, on the host that you're using at any given time. But over time, contracts between software change so that a shared library that worked yesterday, if it's upgraded and an executable uses it may not work with the new shared library, or vice versa. If you upgraded a binary and it tries to use a feature of an old shared library that doesn't exist in that shared library, it won't work anymore. So anyway, you get the idea. And Nix gives us a little bit of salvation from DLL hell. This is why you can install Nix on almost any Linux or macOS system and install most of the packages that exist in the Nix packages repository and have some confidence that they'll work. And no matter what you do to your host system, or by adding other Nix packages to the set of packages you have installed, you're unlikely to break another Nix package on that system. And this is kind of magic. It's why you can install like 8-year-old Nix software on, the most bleeding edge of distributions. You can install Nix on, Fedora 79 and whatever. And it's also why Nix is a much better solution to getting sort of Unixy commands on macOS than something like Homebrew. Homebrew tends to only support, some number of macOS releases over time. And it abandons old ones because it just can't do this. This is not something that is in its wheelhouse. So Nix does some really cool things that lets you build software that you can install non-globally more easily. And what I mean by non-globally here means that multiple versions of the software that you're building can exist on the system at the same time. And each version that you build can have different build time and runtime dependencies. And this is the sort of where the rubber meets the road as far as NixOS goes. There are other systems like Snap and Flatpak, but Snap and Flatpak tend to use containerization to get the same job done. They use operating system namespacing to do that. And what that means is that a lot of times when you run a Snap or a Flatpak, it's in its own little world and it doesn't know about a bunch of the files that exist outside of it. And, you have problems with theming and other stuff and, all the normal stuff. Nix doesn't use the same strategy. It doesn't use any containerization to do its magic unless you want it. You can do that. It's just a little more granular than that. Now this comes at a cost. It's much harder, typically much harder to build software for Nix than other systems. Not really Nix's fault. We've had 60 years of Highlander mentality about shared libraries and support files that, there can only be one on a system. So building Nix packages is largely the task of detecting and fixing these assumptions in the build process software. And this can be very challenging, but we're going to see how it works under the hood, no matter how challenging it is. I'm just going to talk about the details of it and how it works. And then I'm going to go through a short example of how Nix helps you point at specific versions of shared libraries or support files or whatever. So for the record, this is only about C and C++ dynamic libraries using GNU. I don't know beans about other systems. I don't really know that much about C or C++ shared libraries for that matter, but I'm doing it anyway, man. So I'm going to assume you have some experience compiling C and C++ software on other platforms other than Nix. So if you're watching this, I'm sure you already know this, but I have to say it. The unit of software packaging in Nix is called a derivation. And there's a function that exists within the Nix packages library called standard env make derivation to do such a thing. And standard env make derivation is sort of a high level thing. It is a wrapper around a much lower level thing called built-in's derivation. Built-in's derivation is something that will create a derivation for you, but it makes you do all the work. Standard make derivation supplies some niceties like default build inputs, a set of phases, and then hooks that you can use to override different phases, customize build. And if you really want to dive into how derivations work under the hood, Luca Bruno, that URL there, again, you can go find this by clicking on the link to the script in the description. But Luca Bruno has a really, really excellent article about sort of ground up how to use this built-in's derivation function to do the work. But I'm gonna stick to describing things in terms of standard env make derivation because it's just how most people do things. So, in its most simple form, standard env make derivation has some implicit package dependencies. And out of the box, it sort of assumes that you want to build software that has a configure script and a make file in it, which is sort of the auto tool standard for C and C++ files or projects. And standard make derivation implies a set of default dependencies like bin tools, bin utils, libc, gcc, all the stuff that you see on the screen right there, and probably others that I just kind of took a look at this file to see what the dependencies are, but they're basically all the files that you might think of as if you've ever used like Ubuntu or Debian before. There's a build essential, maybe it's called build essentials, I forget, a meta package that pulls in GCC and GNU make and other stuff. It's that set of packages. And when you build a Nix derivation, you typically specify a set of build inputs, which are obviously input, well, not obviously, but they are derivations that your project depends on. They're dependencies, the build time dependencies of the project that you're trying to build. And these are supplied through three main arguments to standard make derivation: build inputs, propagated build inputs, and native build inputs. They're slightly different from each other. It's not really important for this video what the differences are, so I'm not going to go into them, but those are the inputs that it uses. They're typically very tightly specified. There'll be a link to a URL to a tarball that is unchanging, or a tag in GitHub that is unchanging. They're typically not branches, or they're typically not files on the file system, because those can change a lot. This is all about repeatability and being able to build from a known source that doesn't change over time. So that's why it's like that. And so we haven't seen this yet, but in a Nix file, in a thing that uses this make derivation function, the standard make derivation function, you don't name runtime dependencies, which is pretty odd if you think about it. But the reason you don't do that, we name build inputs, and we put both the requirements for building the project, but also the requirements for running the project in our build inputs. And the reason we do this is magic. Nix conflates the build time dependencies with runtime dependencies. And when Nix builds the project, what it does is it goes ahead and builds it all out, And then some, but not all, of the build inputs will become runtime dependencies. Um, for example, like if you supply a build input of GCC, well, that's probably not a runtime dependency of the project, but and it won't be considered one, even though we're not specifying that it's not. Um, and the way that works is that after the software is built, and this is insane in a way, but it's cool, right? Nix, but there's this concept of an output directory for all your files that basically ends. That's where all you put all the stuff that's going to wind up installed on the system. It scans all those files and it basically greps for Nix store paths inside of each file. I mean, even binary files. So in particular, if a binary file requires, let's say that there's an R path or something that is pointed to that has a Nix store path in the R path inside an executable, it will consider that derivation a runtime dependency, the one that's in the Nix store. So, for example, if you have curl 801 as a build input, and the derivation of curl you're depending on has this hash, this is 03, blah 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 blah. If scanning sees the string /nix/store/03 blah 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 in any file, binary or not, it will consider Nix store blah 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 curl 801 as a runtime dependency. Obviously, curl 801 is not important to it because the hash specifies it. But if a build input's hash is found in any output, it's a runtime dependency. If it's not, it isn't. And that's how that works. It does this magical scanning under the hood to see at runtime which libraries and which other derivations do I need. And it sort of truncates the build inputs down to the runtime dependencies by doing that. So here are some links that you can go to see how that works. But that's how it does. So the other bit of this thing is that during build time, the derivations that are build inputs whose Nix store hashes are anywhere in the output files, meaning they're runtime dependencies. After everything is built, Nix goes through this thing and uses this thing called, are we there yet? We're not there yet. But Nix detects all the runtime dependencies, and then for any executable file, any ELF, executable and linkable format file, any shared library, any executable that exists within the output directories, it will add to that .so or executable file in its R path within the metadata of itself. It will add the Nix store path /lib, basically, of any of the build inputs that are considered runtime dependencies. I know that's a mouthful, but just bear with me. We'll see an example of this a little bit later. So RPath, if you're if you're watching this, you know what RPath is, but RPath is basically a list of directories that when you run this file, it will look for shared libraries in. That's basically what it is. So this isn't totally true because some of the detected runtime dependencies are not necessarily like it. I'm not. This is where my knowledge falls off because like there's a bunch of heuristics I don't understand about which ones are and aren't necessary. But basically, it'll shrink the R path down to what it actually needs. Again, I'm not an expert, but to do this, it uses this program called PatchElf, which was written by the main Nix developer, Elko, and Patch elf is used to do both the initial RPath writing and its shrinking. So, in order to get all this done, there's a dependency or a derivation that you can depend upon. I'm not sure it's a derivation, but it's at least something that is accessible in the Nix packages repository called auto patch elf hook. And if it's included as build input, it'll call patch elf. Now, actually, I'm not even sure that this is necessary. I think this might happen just as a matter of course. I said this here that if this is included, but I think it's actually just done by default, as we'll see in a little bit. So, but this is how you make sure it's done if it doesn't work for whatever. So, here is the simplest possible. Now, C++ program that uses a third-party external shared library. Now, it took me a while. I am not a C++ programmer. I just wanted to show something that was demonstrative of what we're talking about here. So inside of here, I have a bool directory, and I think this is exactly what's in here, bool cc. And as we can see, tiny little program that prints hello world, and also happens to use this boolector thing, which is unimportant entirely. It's just a something to include that will cause the compilation of this file to use this third-party shared library. So inside of here we have makefile, and it this is just all me making stuff up, but it's the simplest possible thing. We can call make on this file, and it will compile our bool file to an output name of bool, and it wants the boolector library as specified by this -l flag, and it wants to use the include file that we name up here, include boolector.h, and in order for it to find it, imagine this is not someone not doing this for Nix. This is just somebody doing it on their own, some other system or whatever. So they're not there is a singleton location for this include file, which these people happen to believe will be in user local include boolector. So let's imagine these two files are in this bool directory. All right, and we create a file called bool.targz through that, which I won't do because I've already done it. So now we have a bool targz, and we can create a file. Now we want to package bool at this point, bool.targz into a Nix derivation, and we can make a Nix file that we can run eventually through nix-build that does the minimum required to build this into something that is useful for our demonstration here. The make file of our project here allows us to override the install prefix of the bool file that we generate. So inside of our pre-build here in our Nix file, we export the prefix to say it is the value of the variable out, which under this, when we run this derivation, out will be inside of our Nix store. So we can use nix-build to build our derivation, realize our derivation. This is the fancy term for it. So let's do nix-build, bool.nix. Oh, let me do this. Collect garbage. I forgot to do that before, so we can see it build. This is how you get rid of oh, you know what? I forgot to delete the result. This is how you can get rid of things in your Nix store that are unuseful anymore. You can collect the garbage from them. So it is collecting garbage from my previous run of nix-build for this project. Okay. So now we can do our nix-build again. And it spits out a bunch of junk to us. And let's see, what do I want to say about that? Okay, so as I mentioned before, user local include boolector does not exist on our system, but it's still built. So there's no tests in here, so that would be totally possible for it to build and not work at runtime right now. But it does work. So let me first of all demonstrate there is no such thing as user local. There's not even a user local. It just doesn't exist. So that couldn't have been, our include file could not have been found there. But our nix-build has generated a result in here that has our bool file, the compiled executable that we created through our build. And it'll work. Yeah, it works. It ran. So how did it know? How did it know where to get its include file from? Well, it pulled it from our build inputs. So let's see, bool.nix. Our only build input is this boolector thing, and we can see what it does to under the hood. You know, it does a bunch of fakery. First of all, GCC is wrapped under Nix. It is not the sort of bare GCC command that you would execute on other systems. It is a wrapper for GCC that adds flags to the environment before it actually compiles something. And the same thing with LD, the linker. It does the same thing. It wraps it, and then depending on the build inputs that you have in your environment, it will put different flags on the GCC line and the LD lines to do this stuff. So let me change our bool.nix file, and I'm going to add a line to this, which will let us sort of peer under the hood of our stuff when it is rebuilt. So I'm going to remove that result again. I'm going to collect garbage, so it'll rebuild. It wouldn't rebuild otherwise. Actually, probably would have, because I changed the actual Nix file. But well. Okay, so now we can run nix-build again, and we're going to get a bunch of output in here that gives us some clue about what's happening under the hood when it gets built and why it actually found the include file in the library. Okay, just oops, my mouse isn't working for some reason. So it's probably better to look at it over here because I've sort of elided some stuff from there, and it lets us see the original flags to GCC here. The original flags were lboolector boolcc o.bool, which is correct. After it is wrapped by flags in the GCC wrapper that Nix has, it has a bunch of other stuff in here. And there's even more than this in here, actually. I've elided a bunch of it. But as you can see, it adds a bunch of flags to the GCC call to compile bool. And it also adds a bunch of flags to the loader here. You know, the original flags, right? The original flags were these. Interesting. Seems like a lot of original flags, but yeah, they're here. And but it added the most important things that it adds here are these rpath statements, which point at things that are either the lib directories of things that are either explicit build inputs, like our boolector thing there, or implicit inputs of our bool.nix build inputs of our bool.nix, like which version of GCC we're using, or sorry, glibc, and then also for whatever reason it actually tries to put GCC on the rpath. I think that gets stripped out later, but so as I see here, this is a lot of gobbledygook, but the upshot of all this is really in these last 3 lines, which is sort of like, okay, here's the rpath of these things. When bool is run, it'll find the lib boolector library by virtue of looking on its rpath. And that's how that works. It'll find the include file by virtue of where is it? There it is. No, by this iSystem. And so it fixes up our bool thing to go look in the right places for the include library, or the .h file we need, and also the shared library that we need. Got it? Good. I don't. So the upshot of this is that when the bool executable is built, it is tied entirely to the versions of boolector that we used, the versions of glibc it depended on, and I think those are really the only two major things we have in here. GCC is probably not useful. So we can see this in action by looking at the when we ran nix-build, it created this result symlink, which is actually path. Let's see, path result inside of our nix store directory. It's just symlink there. So if we run LDD against this bool file in here, we will see that yes, indeed, there's an rpath to this boolector file in there. It also happens to have links to our standard C++ standard library thing that was used to build it. Our GCS, I'm not sure what that is, but also the libc version that was used. And then it also has links to the transitive dependencies of boolector in there. So it has the parser that was used for boolector. GMP is apparently used by boolector. And then it also has the SO of glibc down here. So as you can see, it's pretty much tied to all those specific versions of things. And as long as those things do not disappear, this binary will continue to work, which is pretty impressive. And things in Nix are never, unless you remove them by hand, are never removed. They're never changed. It's totally additive. So as long as there is something keeping this derivation alive, which in this case is this result symlink, this will continue to work for all time. Well, unless ABI compatibility in Linux is not kept, but that's kind of a given. So right. So we can actually, yeah. So I won't show that, but so that's basically the whole thing. I know this is a whirlwind tour of how this works, and I'm not entirely comfortable. I mean, I'm totally comfortable with it, but I'm not an expert in any of this. So I'm just reporting from the field, as it were. And anyway, if this helped you, I'm glad. Leave me a comment if you notice any mistakes. Thanks so much.